Seema, and thank you for returning for part 24 of the chapter Thermodynamics. As I promised in part 23, I will now be solving or finding out the lattice enthalpy of magnesium chloride just as we found it for sodium chloride for a little practice and to make the steps and the process clear to you using the Born-Haber cycle. After that, we'll start solving a few numerical problems from the NCERT textbook exercise. So let us start. The question in front of us is that you have to calculate the lattice energy or lattice enthalpy of magnesium chloride. Mg2 positive plus 2Cl negative gives you MgCl2. And you have both the ions in the gaseous state and magnesium chloride is in the solid state. Right? And the different enthalpies are given to us. I have not written their enthalpies for what, because as I solve it you would understand what I am talking of. They are written in the sequence. So let us see what is the reaction. What is the reaction that is taking place? We have enthalpy, lattice enthalpy cannot be calculated directly. You have to go from enthalpy of formation and then follow all the steps for the lattice enthalpy, and then we have to use Hess's law and find out the lattice enthalpy. So what is the first equation that we start with? Let us start with that. The equation that we will be starting with would be magnesium in the solid state plus chlorine in the gaseous state will give you MgCl2, magnesium chloride in the solid state. Okay? And now from this equation or from this reaction we have to start and find out the enthalpy, that is the lattice enthalpy for the formation of magnesium chloride. So in the first step, what happens? Magnesium is present. I'm now making the simplified version of the Born-Haber cycle. In the simplified version, if you remember, I told you in the previous video that I'll be treating these separately. Although there's nothing different between the actual version and the simplified version. The only difference is that I'll be treating these two separately, both the reactants separately, so that it becomes easier for us to understand. Instead of writing the chlorine, we'll be dealing with them one by one. So instead of writing chlorine in every step and then coming to it when we do, I will be treating them separately and we'll be joining them here. Let us start. The first step is that magnesium solid has to be converted into magnesium gas. Right? Magnesium solid is to be converted into magnesium gas. Now, the amount of energy which is given to convert a solid into a gas, or the process, is known as sublimation. So here we'll be using the enthalpy of sublimation. So delta sublimation H. The enthalpy of sublimation is given to us is 120 kilojoules. So I will not be writing the units again, we'll write the units in the end. So it is 120 kilojoules is the enthalpy of sublimation. Now we get magnesium in the gaseous state. So what would the next step be? In the next step, magnesium should lose one electron. Now, in magnesium chloride, magnesium is a di-positive ion, which means it has lost 2 electrons. But it does so in 2 steps. In the first ionization enthalpy, that is the amount of energy required to remove 1 electron, is different from the second ionization enthalpy. And both the ionization enthalpies are given to us. The ionization enthalpy 1 is for the first electron of magnesium to be lost, is 756 kilojoules per mole, and the second ionization enthalpy, I've written it as 2, is 1490 kilojoules per mole. So now magnesium has to be converted into Mg2 positive in 2 steps. In the first step, it will be converted to Mg positive, magnesium positive, gaseous, and for this you will be using the delta ionization H1. And what's the value of delta ionization H1? It is 756 kilojoules per mole. 756. Right? And then Mg positive turns into Mg2 positive. So for this, the second ionization enthalpy is being used. Ionization enthalpy 2. And what is the value of the second ionization enthalpy? It is 1490 kilojoules per mole. So now we have got 1 mole of Mg2 positive ions. What do we require now to form MgCl2? We need 2 moles of chloride ions. Do you see this? We need 2 moles of chloride ions. So We start with chlorine. We have 1 mole of chlorine, and 1 mole of chlorine is in the molecular form. So the 1 mole of chlorine has to break down into 2 moles of chlorine atoms first. So in the first step, we will cause the dissociation or the breaking of bonds of chlorine. So you will have the bond enthalpy. So enthalpy of bond formation or bond dissociation. So H bond. The bond enthalpy of chlorine is how much? It is 248 kilojoules per mole. And if we break 1 mole of chlorine molecules, you get 2 moles of chlorine atoms. And that is what we require. We need 2 moles of chlorine atoms so that we can now make it gain electrons and turn it into the chloride ions. And we will get 2 moles of chloride ions from this. So now that we get 2Cl, so we are not changing this heat because our desired amount was 2 moles of chlorine atoms, and we have got that from 1 mole of chlorine molecules. So in the next step, the 2 moles of chlorine, of chlorine atoms, they gain an electron. So you have electron gain enthalpy, right? So enthalpy of electron gain enthalpy. And electron gain enthalpy for chlorine is minus 368, right? For 1 mole of chlorine atoms, the electron gain enthalpy, because it is the molar electron gain enthalpy. So for 1 mole, the value is given because it is these many kilojoules per mole. But how many moles of chlorine atoms do we have? We have 2 moles. And since we have 2 moles of chlorine atoms, now we will have to multiply this by 2. We'll have to multiply this heat by 2. And then whatever we get, that will give us 2 chloride ions. And these will be in the gaseous state. And that was the intention, to have both the ions in the gaseous state. And now magnesium combines with 2 moles of chloride ions. Magnesium ions combined with 2 moles of chloride ions to give us magnesium chloride. And now this amount of energy, which is given out when they combine, is known as the lattice enthalpy. And this is our question. It is the lattice enthalpy, and this is our question. This is what we are looking for. So what was this reaction? This reaction was basically the formation of magnesium chloride from its constituent elements in their most stable state or from their standard states. So what would be the enthalpy in this overall reaction? It would be the enthalpy of formation of magnesium chloride. And enthalpy of formation here, delta FH, all of them are negatives, you know. They are all standard enthalpies, so the negative should always be there when you're writing the enthalpies. So the standard enthalpy of formation of magnesium chloride is minus 698 kilojoules. Do you see this? So now we've got the Born-Haber cycle, and let me now write down the steps and use Hess's law to be able to calculate the lattice enthalpy. So in the first step, I'm going to write down the steps again. In the first step, we had magnesium solid, and it was getting converted into magnesium gas, right? And what was the enthalpy here? Delta H. Now I'm only going to write down the heat here. The delta H, let me write down delta H sublimation was equal to how much? 120 positive. It's a positive value, yeah? Kilojoules per mole. Again, I'm writing the unit only for the first one. I'll not be writing it for the rest. Then in the second step, magnesium, which was in the gaseous state, it turned into magnesium positive, right? In the gaseous state. And now the enthalpy, first ionization enthalpy, is equal to 756 positive value, right? In the next step, you are starting with Mg positive gas, and it's resulting in the formation of Mg2 positive gas. And the second ionization enthalpy is equal to plus 1490, right? So these were the steps for magnesium. In the next step, we now have chlorine molecules, Cl2, a molecule breaking down into 2 chlorine atoms. And gaseous. Both of these were gaseous. And the enthalpy here was enthalpy of bond formation or bond dissociation or bond enthalpy. And how much is this? It is equal to, again, plus 248, because you have to provide heat to break the bonds. And then finally, we have two chlorine atoms which have to turn into chloride ions. And for this we use the electron gain enthalpy, and since we are from the molar enthalpy is for 1 mole and we are getting 2 moles, we'll be multiplying this enthalpy. So it will be 2 into enthalpy electron gain enthalpy, which is equal to 2 into minus 368, which would be equal to 700 and minus 736 kilojoules per mole, right? So we have calculated all these, and now the next step is where magnesium 2 positive combines with 2 chloride ions to give you MgCl2 in the solid state. This is gaseous, and this is the reaction, and the enthalpy of this step actually is the lattice enthalpy that we are looking for. And what is the overall reaction that took place? The formation, we said that we started with magnesium in the solid state and chlorine in the gaseous state, and it got converted into MgCl2 in the solid state. Now, what is the enthalpy of formation of magnesium chloride? Let us write that down. The enthalpy of formation for magnesium chloride is the delta FH negative is equal to minus 698 kilojoules, right? Now, take a look. This reaction is actually a sum of all of these. How is it so? Let us see. The magnesium solid that is present here is what we want here, and let us see in the products you don't have it. Magnesium gas was formed here and consumed in the next step. Mg positive was formed here and consumed in the next step. Mg2 positive, which was formed here, is used up in this step, and the 2 Cl negatives formed here are used up in this step. Therefore, the 2 Cl that is formed here is used up in this step. So what are you left with? You are left with magnesium solid, you are left with chlorine gas, and MgCl2 solid. So this reaction is actually the sum of all of these. Therefore, the sum of all these energies is equal to this. So if you want to find out one of these, then the total energy minus the sum of all the remaining energy will give you the lattice enthalpy. So that is what we are supposed to do now. So what is lattice enthalpy? Delta H lattice. Delta lattice H is equal to, it is equal to the total energy, that is minus 698 kilojoules minus all of these will give you the lattice enthalpy. So minus 120 kilojoules minus 756 kilojoules minus per mole, it's all for per mole, minus 1490 kilojoules minus 248 kilojoules minus 736 kilojoules. Do you see this? So what have we done? This is the total energy minus the sum of all, or minus or subtract all these energies from it, you will be left with the lattice enthalpy. So the lattice enthalpy, when you calculate this, the lattice enthalpy comes out to be equal to minus 2576, which is equal to minus 2576 kilojoules per mole, right? So this is how you would calculate the lattice enthalpy for magnesium chloride. And remember, in India again, when we say lattice enthalpy, we mean enthalpy of dissociation, not association. So, and not formation. So this is not, we will have to reverse the sign to talk of lattice enthalpy if we are using this value in any other calculation. So lattice enthalpy standard lattice enthalpy of formation for magnesium chloride MgCl2 would be equal to plus 2576 kilojoules per mole, right? It will be a positive value for all calculations, although this is enthalpy, lattice enthalpy for formation, and this is enthalpy, lattice enthalpy for dissociation. And now this was how you would calculate the lattice enthalpy for magnesium chloride. Let us now solve a problem from your NCERT textbook exercise. Give me a minute. Okay, so now this is question 6.5 of your NCERT textbook exercise. Let us see what the question reads and then we'll solve it. The enthalpy of combustion of methane, graphite and dihydrogen at 298 Kelvin. 298 Kelvin is the standard temperature. It means that these enthalpies are standard enthalpies of combustion. So the standard enthalpies of combustion of methane, graphite and dihydrogen are minus 890.3 kilojoules per mole, minus 393.5 kilojoules per mole and minus 285.8 kilojoules per mole respectively. Enthalpy of formation of methane will be, there are four options given. So the question is that you have to calculate the enthalpy of formation of methane from the enthalpies of combustion of these three fuels. So let us first write down what we know, and then from that we'll proceed with finding out the enthalpy of formation of methane. We have been given the enthalpy of combustion of methane, graphite, that is carbon, and hydrogen. So let us write down the equations. Methane, when it burns, gaseous methane, when it burns in oxygen, it results in the formation of carbon dioxide, CO2, and H2O. So there will be 2 H2O and 1 mole of methane we are taking. And there should be 2 moles of oxygen. And what is, for this, what is the enthalpy of combustion? It is the amount of heat which is given out when 1 mole of a substance burns completely in oxygen. So what we have to keep in mind in the equations is that you should have 1 mole of the fuel, that is 1 mole of methane, 1 mole of carbon and 1 mole of hydrogen while writing these equations. So in this step, what is the enthalpy? Delta H here is of combustion is minus 890.3 kilojoules per mole, right? Now, in the second equation, what do we have? Graphite. Graphite is carbon, solid, and it will be in the gaseous state when it is burning, plus oxygen will give you carbon dioxide, okay? And the enthalpy of combustion here would be equal to 1 mole of carbon is burning completely in oxygen to give you 1 mole of carbon dioxide, and therefore the enthalpy of combustion here is minus 393.5 kilojoules per mole. Why is the enthalpy of combustion negative? Because it is the amount of heat given out. Whenever heat is given out, the value is negative. Heat being lost by the system. The next is hydrogen. Hydrogen combines with oxygen. It burns in oxygen to produce water, H2O. So how much? For 1 mole of hydrogen, there should be half a mole of oxygen to give you 1 mole of water, because enthalpy of combustion is for 1 mole. And this turns out to be how much? The enthalpy of combustion for hydrogen would be equal to minus 285.8 kilojoules per mole. Now, what is the desired reaction that we need? We have been asked to find out the enthalpy of formation of methane. So let us now write down the equation that we are looking for and then see what are we to do about this information that has been given to us in the question. So the overall reaction that we are looking for is the enthalpy of formation. What is enthalpy of formation? It is the amount of energy given or taken in the formation of 1 mole of a substance from its constituent elements in their standard states. So how is methane formed? Methane would be formed from carbon and 2 moles of hydrogen. So carbon, the overall reaction we'll say is that carbon combines with 2 moles of hydrogen, because we need 4 atoms of hydrogen to produce CH4. And this enthalpy of formation is our question. Or we could say that this is the desired reaction. If this is the desired reaction, what do we have in these equations to get, what do we do about these equations to get this desired reaction? We want carbon in the reactants, and we want methane in the products. So in the first equation, we have methane in the reactants. So the first hint that we get is flip it. Flip this reaction. So we will flip the first reaction. This is 1, 2, and 3. So we'll flip the first reaction to get the fourth reaction. That is, when you flip this, you will have carbon dioxide plus 2 moles of water will give you methane plus 2 moles of oxygen. And this energy, the enthalpy here of this reaction would be, the sign would also become opposite. The value remains the same, but it becomes positive 890.3 kilojoules per mole. Right? Now, the amount of energy remains the same, only the sign changes. This was energy given out, now this is energy absorbed in the opposite process. Now the question is, what is it that we need? We need how many oxygens? Methane and hydrogen. We do not need oxygens at all in the final reaction. So whatever oxygen is participating in the reactions, in the different reactions, we have to eliminate it. So whatever oxygen is used in the reactants should be there in the products to cancel it out, so that we get our desired equation. So let us look now, how can we do that? First of all, what do we need in the raw materials? We need carbon. Let us just circle them. We need carbon. We need hydrogen. But hydrogen, how many moles do we need? We need 2 moles of hydrogen. And we have only 1 mole of hydrogen in the reactants. Do we have it in the products? No. So we need 2 moles of hydrogen. So this equation, entire equation, should be multiplied by 2. This entire equation should be multiplied by 2. If you multiply this by 2, everything will multiply by 2, which means you will now get 2 moles of hydrogen, 2 moles of hydrogen, half a mole of oxygen into 2 will become 1 mole of oxygen, and water also multiplied by 2, you will get 2 moles of water. So what happens to the heat? When you multiply this entire equation by 2, the heat also should be multiplied by 2. So now I'm just removing this so that you know that we have multiplied this entire equation by 2. And the heat should also be multiplied by 2. When you multiply this heat by 2, it comes out to be, this would become 571.6 kilojoules per mole. Okay? On multiplying it by 2, this will become equal to 571.6. And it's a negative value, negative 571.6. So now let us see what are we left with. Now this is an equation that we are not using. Find out the sum of 2, 3 and 4. You will come to the final equation that you want. Carbon is present here. You have 1 mole of oxygen and 1 mole of oxygen here, which makes it 2 moles, and there are 2 moles of oxygen in the products that are cancelled. Okay, you have 2 moles of hydrogen, we want that. You have carbon dioxide in the reactant and you have carbon dioxide in the product, it is cancelled out. You have 2 moles of water in the products and 2 moles of water in the reactants, they are cancelled out. So you're now left with what you want, the desired equation. Now that you've got the desired equation, the enthalpy, when this equation is actually the sum of these 3, then the enthalpy of this equation should also be the sum of the enthalpies of all these 3. So according to whatever changes we've now made, the sum of these would be my enthalpy of formation. Standard enthalpy of formation for methane would be equal to minus 393.5 kilojoules per mole. And you have to add this, which means the minus remains minus. minus 571.6 kilojoules per mole. Okay, we are adding these. So you can say it is plus, minus this, plus the last one, that is 890.3 kilojoules per mole. When you solve all of this, you come to the answer that is minus 74.8 kilojoules per mole. This is your answer. And this is the answer that you will choose. Let us now come to the next question. Question 6.7 of your NCERT textbook exercise. What is the question? In a process, 701 joules of heat is absorbed by a system. If it is absorbed by the system, it means the sign of the heat should be positive, right? And 394 joules of work is done by the system. By the system means the amount of energy which is being used for work is being lost. Therefore, you will have a negative sign. Work done by the system has a negative sign and work done on the system has a positive sign. Similarly, heat absorbed is positive and heat lost is negative. So, this information we know what are the signs for both the heats. Of work is done by the system. What is the change in the internal energy for the process? We know internal energy is delta U. The change in internal energy is equal to the change in heat, the sum of heat and the work done. Now, the heat we know is plus 701 joules of heat and plus the work done is minus 394 joules of work. So when you solve this, it comes out to be equal to 307 joules. 307 joules of work. The change in internal energy is plus 307 joules, which means that 307 joules of energy, internal energy, has increased when 701 joules of heat is absorbed by the system and 394 joules of work is done by the system in a certain process. So this was question 6.7. And with that, I'll finish this video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching and bye-bye for now.